All right, so for today, we're still working with radicals, and we're looking at complex numbers. Complex just means it has an I. That's all it means. We're going to look at different arithmetic operations. What's that mean? What's arithmetic? Oh my gosh, you guys, what's arithmetic? You learn it in like grade school. Yeah, it's basic math. Adding, subtracting, multiplying, and dividing. That's all it is. We've already done dividing with radicals and stuff, so we're actually going to only look at adding, subtracting, and multiplying. Yeah. Yay, right? We can do this. That was a cheer and a yawn combined. It was nice. All right. So first thing, guys, we're going to look at is adding and subtracting radicals. So like radicals, kind of like terms, would be like 3 radical 5 and 7 radical 5. The radical almost acts like a variable when we're doing adding, subtracting. So unlike radicals would be like 4 radical 3, 5 radical 2. The radical parts are different. We cannot put those together. Okay, so the number under the radical has to be exactly the same in order for us to add and subtract them together. Okay, so, but sometimes you may need to simplify the radicals. Because if you have like a radical 8 sitting there, could you do a factor tree and simplify that? Yeah, so you still want to look for, can I do a factor tree and find some pairs to simplify? All right, so number 1, radical 3 minus 5 radical 3. Are they like terms? Yes, they are like terms because they're both radical 3s. What number is in front of this first radical 3? So what is 1 radical 3 minus 5 radical 3? Beautiful. Look how hard math was today, you guys. It's nice when the radicals are already the same. It's very little work. But what about number 2? Stays the same. Yep, it almost acts like a variable where you're just combining them. How many do you have? So number 2, 4 radical 7 plus 2 radical 28. The way they sit, are they like terms? No, but can you simplify one of those radicals? Or both? Yeah, I can simplify radical 28. If you do a factor tree, so that's 7 and 4, and then 2 and 2. That corner of my board, for whatever reason, my marker always changes when I write up there. All right, so we get, it's so weird. Pair of 2s. And then what about this other 2 that's already here? Multiply it, so that's going to make that 4. And then what was the leftover in the fridge? 7. All right, so we simplified the radical 28 to 2 radical 7, but there was already a 2 there, so it became 4 radical 7. And now 4 radical 7 plus 4 radical 7 is 8 radical 7. Yeah, the number under the radical when you add stays exactly the same. Mm-hmm.
So, if you simplify
where I got 4 radical 7? You're not understanding how I went from here to here?
Yeah.
I did my factor tree on 28. That's what's up here. And then I had a pair of 2s, but I also had a 2 already here. So 2 times 2 was 4. And the only leftovers in the fridge is 7. Yep, so I just did my factor tree. All right, number 3. Are those like terms? Nope, at least not the way they sit. So we need to check and see. If I do factor trees, simplify my radicals, will they be? I'm kind of working my factor trees up just so I can have more room working down. So 32, 2 and 16, 4 and 4, 2 and 2, 2 and 2. All right, so looking for pairs. I have a pair of 2s and a pair of 2s, which is 4, times the 5 already in front, 20. Leftover, 2. So radical 2. All right. Minus, now I got to figure out this one, 18, it's 2 and 9, 3 and 3. So I got a pair of 3s, times the 4 in front, gives me 12, and I have a leftover 2. Now are they like terms? Yeah. Okay. So I have 20 radical 2 minus 12 radical 2 gives me 8 radical 2. So number 4. Are they like terms the way they sit? Nope. So we need to go ahead and do our factor trees. So you guys go ahead and simplify yours. I'll simplify mine. I won't say anything, okay? We'll see what we each get. All right, so when you do your factor trees, we end up with negative 8 radical 6 plus 14 radical 2. Are they like terms? So what do? I just leave it. They're not like terms. I can't do anything with that. Now, I did simplify it as far as I could, but that is as far as I can go. So they don't always end up matching, okay? But if they do, great, put them together. If they don't, all right, you simplified them, but that's as far as you can go. All right, so let's talk about multiplying radicals. Have we already done some multiplying with radicals? Yeah, we have. So when you multiply radicals, you don't have to have like terms, right? We talked about that earlier. So people always confuse when do I need to have like terms and when don't I? So when do you have to have like terms? Adding, subtracting. When don't you? Multiplying and dividing. Okay, so you just need to kind of keep that straight. Multiplying, they don't have to be alike. So for here, if I ask you to multiply this, that's you have to distribute this, right, to both parts. So what's radical 10 times radical 6? And what's radical 10 times 3? Ooh, very good. 3 radical 10, right? It's like you got the inside numbers, you got the outside numbers. You got to keep track of which ones multiply. Do I stop there? Am I done? I can break it down. Good. Right, that radical 60, I can do a factor tree on that. So 6 and 10, 2 and 3, 2 and 5. So I have a pair of 2's. Leftover 3 and 5, so 15. Factor tree on the 10. I get 2 and 5, so no pairs, it doesn't help me. Plus 3 radical 10. Can I add them together? No. You have to have like terms when you add, and I do not have like terms. So as far as I can go is just to simplify that 60, but that's it. All right. So why don't you guys try number 5? Just 5. All right. So when we distribute radical 2 times radical 6, it's radical 12. Radical 2 times 5, 5 radical 2. Again, be careful. A couple people are still multiplying every single time. If one's in, one's out, they don't actually multiply. All right, I can do a factor tree on 12. All right, so we end up with a pair of 2's, leftover 3. Can't do any factor tree there. Are they like terms I can add together? No. One's a radical 3, one's a radical 2. They are different. So that is where we should have stopped. Majority of you looked really good on that one. Now, number 6. What word comes to mind for how to multiply that? Somebody said distribute. That's the word I want to hear. But I know that's not the 4-letter word that most of you usually say. What? See, now, she said FOIL, which I agree, that's the word I was looking for, but I don't ever want to hear that word in my classroom. If you've never heard of it, great. Honestly, I usually end up yelling at people saying that you're cursing at me because that's a bad word in my classroom. FOIL. I do. The reason I hate that word, let me explain why, because some of you are like, why? It's great. Help me learn how to do that, right? It works if you have like x plus 2 times like x plus 3 or x plus 4, right? Like that's first, outside, inside, last. That's how a lot of you memorized. But what if I was multiplying like times something like this. Does first, outside, inside, last make sense anymore? No. It bothers me because it only works if it's 2 terms by 2 terms. What happens if I have 2 terms times 3? Then suddenly you have no idea what to do with it. To me, all you're doing is distributing, right? You're just taking this first term and it multiplies to everything over here. And then you take the second term and you'd multiply it to everything over there. You're just distributing, okay? You don't need a fancy 4-letter word that's going to make me yell at you for cursing, right? Okay, it's a bad word. Don't say that, Mary. All right, so we're going to distribute for number 6. Go nice and slow because there's a lot of pieces with a lot of things going on here. So we're going to distribute the radical 5 first. Radical 5 times radical 15 is radical 75. Good. All right, and we're going to distribute to the other term. Radical 5 times negative radical 3. Perfect. Negative radical 15. Make sure you watch your signs. If you mess up anywhere, it's just usually because you miss a sign. All right, now we have to distribute the second term. 2 radical 3 times radical 15. Good. 2 radical 45. 3 times 15 is 45. And then 2 radical 3 times negative radical 3.
No, because you do radical 5 times radical 75.
Quinn, you always take the first term, multiply it by both parts over here, and you take the second term and multiply it by both parts. This is all the answers I'm getting as I multiply. And then we're going to try to add those together or simplify those. What's 2 radical 3 times a negative radical 3? Let's take it real slow. I know some of you can do more in your head. But what's 2 times the negative 1 that's here? It's negative 2. And what's radical 3 times radical 3? It is 3. Now, if you wrote down radical 9, fine. You're just going to do it in another step. Totally fine. Whatever works for you guys. All right. Now if you have a 9, that's in a radical. But if you wrote 3, it's not in a radical. Because technically radical 3 times radical 3 is radical 9. And the square root of 9 is just 3, not radical 3. All right, so now we got to try to clean this up a little bit. Because the way it sits, nothing's the same. Can I do a factor tree on 75 and find some pairs? Yes, I can. All right, that's 3 times 25. And then 5 and 5. So we got a pair of 5s and a leftover 3. All right, radical 15. If I do a factor tree there, do I find some pairs? On 15? Because 15 is just 3 and 5. No pairs, so that's going to stay minus radical 15. 45. Yes. That's 9 and 5, which is 3 and 3. 3 times the 2 that's already there. So that's going to give you 6, and then radical 5. Yeah, just be careful when you got those extra pieces already out front. And then 2 times 3, it's going to be minus 6. Do we have any like terms? No, I got a radical 3, a radical 15, a radical 5, and then just a 6. So actually nothing ended up being alike, but it is simplified. That would be where we stop. Right there. Okay. Sometimes you do that and you find things that are alike and you put them together. And if there's not, you just leave them be. All right. Try number 7. All right. So we're going to distribute. So we have radical 6 times 4 radical 3 should give you 4 radical 18. Radical 6 times negative 3 radical 6 is negative 3 radical 36. We'll just go one step at a time here. All right, distribute the next term. So negative 2 radical 3 times 4 radical 3 is negative 8 radical 9. And then negative 2 radical 3 times negative 3 radical 6. 2 negatives make a positive 6 radical 18. All right, that's where your first step should have been, just by distributing. All right, some of you I think recognize, hey look, these are like terms. right? So we had 10 radical 18. And then square root of 36 is 6 times negative 3 is negative 18. Square root of 9 is 3 times negative 8 is negative 24. I'm pretty sure I saw somebody's paper had that exact answer right there, which is great. But is it done? It's not done. Because, well, one, I have like terms right there. Right, negative 18 minus 24 is negative 42. And then here, I can do a factor tree. That's 6 and 3. So we get a pair of 3s times the 10 that's there is 30. And I have a leftover 2. And then those are no longer like terms, and they are simplified. I am done. Was it right? Yes. Okay, I think a lot of you were on the right track. You just didn't keep simplifying as far as you probably should have. All right, before we get to the next problem, let me ask you a question. What is 3 squared? Why is that 9? Because that means 3 times 3, which gave you 9. Okay, what's 5 squared? Why? Okay, so what is the square telling you to do? Multiply by itself. Okay, keep that thought in mind. Look at the next problem. What's that mean? It is not. Angel? Yeah. Good. You're multiplying it by itself, right? So what you did down here, 3 squared meant I multiplied 3 times 3. Radical 11 minus 2 squared means I have radical 11 minus 2 times radical 11 minus 2. Means I have 2 of them. Right? That's what you told me down here is what the square meant. You multiplied it by itself. Same thing, you multiply it by itself. Is it what? Huh? Squaring a binomial. I used to have a picture when I taught in Findlay. I was allowed to paint on my walls, and I had painted this picture of a guy hanging upside down. He's like chained like to the wall upside down, like his hair is like falling straight, you know, because he's upside down. And it said it was the penalty for squaring a binomial and forgetting the middle term. What that meant was it's for people who did exactly what he said. Oh, it's 11 minus 4. No. It means you have to multiply them by each other and then kind of do all the whole thing. So, in other words, the penalty for doing what he said is to hang him upside down on my wall. So, you have that to look forward to. Yeah? All right. But anyway, anytime you see something squared, that means you take that and you multiply it by itself. You have 2 of them. So what if it was cubed? What would that mean? You'd have 3 of those pieces. We're not going to get into that today, but just so you're aware, the exponent tells you how many of those you're multiplying. All right, so then we're going to multiply. So radical 11 times radical 11. Radical 121 or just 11. So whatever. I'll write radical 121. If you're comfortable to just write 11, just write 11. Radical 11 times negative 2. Negative 2 times radical 11. Negative 2 times negative 2. Positive 4. Good. All right, and we know that the square root of 121 is 11. I'm lazy and don't want to rewrite everything. So that's 11. All right, like terms, I have 11 plus 4, which is 15. And then I have negative 2 radical 11 minus 2 radical 11. Negative 4 radical 11. Can I simplify my radical at all? No? So I am done. When you add 2 negatives, it's still negative. If you were multiplying 2 negatives, it makes positive. So we always think about with adding and subtracting, if you owe me $2 and you owe me $2, you owe me $4, right? You still owe me those dollars. Okay, so in my mind, I always think like, I'm telling you, basic math can be summed up in talking about money and cookies. Everything I can relate back to that, and you're like, oh yeah, makes sense. Okay, money and cookies always comes back. All right, questions here though? If you're anything, you're going to mess this up. You're just going to forget that that means you have two of them. Always stop and think what it means to square something. All right, what if I add and subtract complex numbers? Complex just means I have an I. Does it really change much? No. I, just like those radicals, acts like a variable. So anything that has an I with it, they're considered like terms. Now, the way these are written throws students all the time. I need you to really stop and look. In this first problem, what am I asking you to do with both of those parts? Add them. So are the parentheses necessary? No, they're really not. So if it's up to you, if you want, kind of cross them out or erase them, rewrite it without them, whatever you need. They're not necessary because I'm adding. Parentheses aren't necessary. I have some students, every time they see parentheses, no matter what symbol's in between, they multiply them every time. Very, very wrong, okay? That's way more work, too. So what's -5 and 6? What? 1. Good. And then I have 8i minus 4i. A positive 4i. Ta-da! That's it. Okay, the second one. Are the parentheses necessary? No, it's just an addition problem. So just put your like terms together. 7 minus 3. And -2i plus I. It's -i. Yeah, adding, subtracting with i's, way easier than radicals, right? Radicals can have lots of different numbers under them. There we go. What about the third one? Are the parentheses necessary? The fact that I didn't just go run to the board and finish this problem tells you that they are important, okay? What does it do when there's a negative in front of a whole piece of something? What do you have to do with that negative? You have to distribute that negative, right? It's kind of like there's a -1 sitting here. So does this first one change? No. Think about, we read from left to right. It's the same way we think about math. From left to right, there's nothing in front of this to distribute that changes this. This is still going to stay -10 minus 3i. That doesn't change. But here, the minus in front distributes. So -1 times 4 is -4. And -1 times -9i is a positive 9i. So there, that second parenthesis made a difference. Now, if you're someone like, how am I ever going to remember that? Think about them all that way. So if I come back to this one, there was no number in front, so I didn't have to worry about distributing anything. Here, let's say I use the same idea I did down here. If I distribute a +1, does it change it? No, it doesn't change it. So if you want to use that same thought about whatever's in front I distribute, it works all the way through. Just distributing a +1 doesn't change anything. Distributing a -1 changes it. Okay? So now I can put my like terms together. -10 minus 4 is -14. -3i plus 9i plus 6i. And that's it. I guarantee, I'm going to go with 3 of you at least. We'll mess that up when it comes time for your test. Don't be that person, okay? You got to really stop and look, because I would bet at least 3 of you will distribute that entire thing. Like, we'll actually come up and like distribute the -10, and you'll distribute the -3i. That is not a multiplication problem. That's a subtraction problem. You have to distribute the negative, but that's it. All right, so why don't you guys try this top one? Actually, how many's on here? Just the 2? Do both of these. All right, so the first one, do I have to distribute anything? Yes. Now, into the first one, nothing's going to change. That's still going to stay the same. Here, since it's negative, we have to distribute the negative. So negative 1 times negative 2 makes that positive 2. Negative 1 times 4i is negative 4i. Now I can put my like terms together. Okay, so negative 5 plus 2 is negative 3. Negative 3i minus 4i. You owe me 3, you owe me 4. You're still going to owe me. Negative 7i. Yeah, just watch those signs. All it takes, guys, in math is one sign to mess up your entire problem.
What is that eye?
It's an eye with a tail on it?
Yeah, but you said it looked like a J. I thought it looked like a U. And I was like, well.
Better?
Yeah.
All right, second one. Did you have to distribute here? No. If you really wanted to, you could, but distributing a positive 1 doesn't change anything. All right, what's negative 3 plus 3? Nothing. 9i plus 9i? Is that it? That's it. 18i. Yay, good. We all right? They look pretty good walking around. All right, last 4. You guys ready? Last 4 of adding and subtracting. First one, do you need to distribute anything? No. You know what? Let's get you guys up here. Forget me doing this all the time. Who wants to come up? Come on up. The first one.
All right, so got your numbers. Like, yeah. Okay. So you don't gotta distribute this with the plus. I mean, you do, but
Does it change anything?
no.
Nah, it doesn't change anything.
This is how it is. So you got negative 7. What's negative 7 plus 6, everybody? Negative 1. No, yeah. That was right. And negative 9i. Negative 3i. Is negative 12i. Wow.
Is that it? It's really that easy?
I think so.
Yeah, it really is. Yeah. All right, who wants to do the next one? Yeah, come on up, Chris.
This little guy right here.
Well,
Don't see him.
we did see him. There you go.
All right. One right there, and this is gonna cancel that out, make it a positive. That is a plus sign.
Got that?
Good.
What's that become?
This becomes a negative sign.
So he's taking lazy mathematician to the next level, is what he just did. So when he distributed the negative, 2 negatives made that a positive 4. Negative 1 times 2i made that negative 2i. He just didn't rewrite it. I can appreciate that. I got it.
And you got so add negative 5, you add 4, and you take that and subtract 2i. That's 11. That is not what I wanted. There you go.
Very nice. Very good. Makes you guys appreciate my teaching a little more, doesn't it? All right, so who wants to do the next one? Come on up. You guys are explaining, which makes me happy. Usually I gotta drag words out of people.
This one's really easy. Negative 2 and 2 is nothing. 5 plus 5 is 10, so you have 10i.
Why didn't you have to distribute?
Because it's a plus sign.
Very good. Man, that was an easy one. All right. Last one. Last chance. Somebody who's not been up here. Where's my girls at? Come on, girlies. Really? No one? You know what? Dylan, pick anyone you want to go up there. They don't have to volunteer. If if you need to bring your paper or your calculator with you, you're more than welcome to. All right, guys, why don't you, while you're waiting, try the last one on your own. Let's see if you get the same thing that she does. All right. You can do this, Angel. And you know what, guys? If you come to the board and you mess up, so what? We'll learn together, okay? She broke it.
Literally after you say you messed up.
You're totally, you just hit that black bar at the bottom and it just, yeah, you're fine. Guys, I expect you to be even more respectful to your classmates than you are to me, okay?
Nobody's ever said it before.
Good. Good. She distributed the negative. That is perfect. Very nice. Okay, like terms, once you distributed the negative, put them together, -2 plus 6i. How are we feeling with everything we learned today?
Tired but good.
Tired but good. Is that a good statement for the rest of you? Chris is the only one talking to me today? Thanks, Chris. I appreciate that.
Still